Hi again, and welcome back to the second part of 3 of Lecture 4 in the Galaxies course at Stockholm University, fall term of 2025. In these last 2 parts of the lecture, we are going to foray into the world of star-forming galaxies. In the first, we will revisit the world of spiral galaxy morphology, and in the second part, we will take a further look at stellar populations. If we remember looking at the Hubble-de Vaucouleurs tuning fork diagram of galaxies, and we take a little closer look at the right side of the diagram where we have the star-forming galaxies, we remember that from the top to the bottom, we move from unbarred to barred galaxies with intermediates in the middle. And when we move from the S0 to the SD, we move basically from more tight, well, S0 are lenticular, but SA are more tightly wound spiral arms, more dominating bulges, and so on. And finally, out here, we also have the irregular galaxies. In the middle, there are also what we call the Magellanic types. The Magellanic types are galaxies, spiral galaxies, disk galaxies that have been interacting, that have been colliding with either other galaxies or other large gas systems and so on, which has broken them up, but not so much that they are not still recognizable as spiral galaxies. So they're kind of an intermediate type between the spiral galaxies and the proper irregular galaxies. The disks of star-forming galaxies contain gas. That is, of course, a very important characteristic. It is the gas, after all, that makes it possible to form stars. Another important characteristic is that almost all kinetic energy in disk galaxies are in the form of ordered rotation, which means that these are what we call dynamically cold. In contrast, if we look at elliptical galaxies, you will see that there the stellar orbits are more or less random. So if you look at any small neighborhood, any small region in an elliptical galaxy, the stars closest to you, the stars most nearby to you, are likely to have a very, very high, very strongly varied distribution of velocities. They will be going quite rapidly relative to you, and they will be going in more or less random directions. On the other hand, in a disk galaxy with a lot of ordered motion, there might be as much total kinetic energy as in the elliptical galaxy, but in any given point you find yourself imagining you are a star somewhere in this galaxy, you will see that the other stars are moving along with you, so that if you look at your own little neighborhood, the relative motion between these stars will be very modest, and that is why we call them dynamically cold. If we revisit again the S0 to SD sequence, we see that the S0, the lenticular galaxies with or without a bar, have basically no spiral arms, but very large bulges. And as we move further out the sequence, the bulges grow smaller and less dominant. The spiral arms become less tightly wound. And you will also see more and more cold gas present in these galaxies as you move out this sequence. You will also see that they move from higher mass here to lower mass galaxies here, although there is a quite large spread in this tendency. The geometry of the spiral arms is defined by what we call the pitch angle. This is the angle at a radius r between the spiral arm of the tangent to the circle of radius r. So what does it mean? It means that if we have a spiral arm here, and at a given radius, for example, here, we also draw a circle of the radius, the same distance, then the angle between the tangent to the circle and the tangent to the spiral arm is the pitch angle I. And of course, if you have a large pitch angle I, that means that you have very loosely wound spiral arms. If you have a very small pitch angle I, that means you have very tightly wound spiral arms. Spiral arms can be either leading or trailing, which you see here. If this galaxy system is rotating in this direction, then we call the spiral arm here trailing. Or if it is rotating in this direction here, we call the spiral arm here a leading spiral arm for obvious reasons. And again, as I said before, decreasing pitch angle I means tighter wound spiral arms. Here we see a relatively large pitch angle SD type galaxy. Here we see an SAB, so in between A and B type galaxy with more tightly wound spiral arms, and also, as we saw before, a much more pronounced bulge in this galaxy compared to the one over here. Of course, as with all other kinds of classification, there's always the odd one out that never quite fits in these qualifications. Some galaxies do not have these neat spiral arms, but still have a clear, you would say, spiral arm pattern, even if you cannot follow each individual spiral arm. And these are what we would call flocculent galaxies, which have patchy spiral arm patterns rather than large coherent spiral arms. This is one example of such a flocculent galaxy. It's an SA type, you can see. And you can also see this has a very large and very prominent bulge in the center. So what are spiral arms? Where do they come from? Initially, of course, it is very straightforward to just think of them as assemblies of stars that travel together. But it turns out that this is not really possible if you take a closer look at it. And that's what we're going to do here. So if you imagine, this is what we call the winding problem. If you imagine that you start out with 4 stars that are lined up from the center and out, and then they start following the general rotation of the galaxy. What happens is that the rotation, due to Kepler's laws and so on, the rotation of these is much faster in the center than they are further out. So that means that as time passes, you can see that the first one will already have, once the first one has finished its first half lap, the one here, the ones further out, will still barely have made any strides and any inroads on their first lap. As the first one has done its first full lap, the outer one, the D one, is only 1/4 lap through yet, and the other ones are also struggling to keep up. And it's quite clear that as this goes on, you get a more and more tighter winding, and it wouldn't take very long before this structure of stars would be completely erased, because these stars are, of course, not tied together by a line. They just happen to be aligned from the start. But how do you tell at this point here, how do you tell that these stars are actually aligned more than any other stars that happen to be in the neighborhood of these ones here? You don't, is the answer. So clearly the spiral arms are not just something as simple as physical structures or like individual stars that happen to be travel companions. There's something else at play. There's more that you can read about this winding problem in chapters 8.3.3 and 10.1.6 in the course book. So this winding problem was something that people found out quite early on and quite quickly. So already way back, people needed to come up with a different explanation. This is back in the, if I don't misremember, back in the 1940s, 1950s. And what they instead came up with was the theory of density waves, which today has been observationally confirmed many times over. So what it says was that instead of structures of stars that are traveling together, what if the spiral arms are actual density waves that travel through the galaxy's gas, leading to waves of star formation and also to waves of higher density of stars in the disk? So what happens in the density wave theory is that gas is compressed in a moving wave that kind of moves through the disk in a rotating, sweeping pattern. This wave has a pattern speed. So that is the speed at which the density wave pattern travels, which is not generally the same as the local orbital speed of the gas of the stars in the galaxy. So if you imagine that the orbital speed is faster than the density wave pattern, and you imagine that you are a star somewhere out in the disk, what you would see was basically the same as if you're out driving and then you're suddenly hitting a patch of heavy traffic. The cars will suddenly become closer to each other. Everything will go closer. You will spend quite a lot more time in this before you eventually get through it, and you can speed up and keep up moving, and there will again be further between the cars and you will be moving at a higher speed. But it can also happen the other way around, that the pattern speed is faster than the orbital speed, where something similar will then happen, but the density wave will come from behind you and overtake you instead. So basically the opposite of a traffic jam, I guess you could say. So in this scenario, because of the gravity, the stars spend more time near the density peak. So there is an actual higher density of stars. However, this is perhaps not the most dominant reason why we see the spiral arms, because the higher density of stars is not a super strong effect. It is there, but it is not the strongest one. But the high density gas also leads to a wave of star formation. And star formation means more stars and younger stars. Younger stars means brighter stars. And brighter stars are way, way more visible than just a slight peak in the density of the less bright stars. As we remember from before, the younger stars are more massive. They are much, much brighter than the less massive stars. And they also live much shorter, right? So the younger stars that are formed do not have a lot of time to like disperse out into the disk the same way that the more low mass stars can. So they live and die inside these density waves, leaving only a less luminous population of stars behind that is more smoothly distributed through the disk. So therefore, the spiral arms are more pronounced in blue and ultraviolet wavelengths, but they are also visible in the infrared light. What we see here is our old friend Messier 51 or M51. Here it is observed with the Hubble Space Telescope, and you can see that there are young stars in blue. There are these H2 regions of ionized hydrogen in red. These are basically the regions where active star formation is happening. And you can also see the dust that is created by these very young stars, and this young wave of star formation also follow the general patterns of the star formation and the density waves. But underneath, if we looked at this galaxy in near infrared, we would probably see a much more smoothly distributed stellar population, but still containing density waves. which is something we actually saw in one of the first lectures. If you remember, I showed how different the galaxy could look at different wavelengths. And what we saw was that the spiral arms in the near infrared were much less pronounced, much less prominent than they would be in the ultraviolet or in the H-alpha, which is tracing these regions of hot gas where stars are formed. Here we have the same galaxy rotated 180 degrees, I believe, but what we are tracing here with the blue color is the giant molecular clouds. And you can see that these also, as expected, but still kind of impressively, very neatly follow the general pattern of the spiral arms where all the star formation is happening. Another very prominent part of the morphology of a spiral galaxy is the bulge, or the spiral galaxy, or late-type galaxies in general. And as we have seen before, not all bulges are created equal. We see 4 examples here. One face-on galaxy is M91, which has a nice and large prominent bulge and also a very nice and clear bar here in the center. And then spiral galaxy, a spiral arm spiraling out from around the distance, the radius of the bar. And then we have 3 edge-on galaxies, and I think these very nicely show some of the diversity we can still see in the population of late-type galaxies, spiral galaxies. We can see one here that has a very thin disk with some quite clear dust lanes in light here. And you can see that there is a quite prominent bulge, but you can also see that there's a very prominent thick disk. So there is a secondary population of older stars, which is quite prominent in this galaxy. In this galaxy, by comparison, we also have a reasonably prominent bulge. We have a thicker, thin disk, but much less prominent of a thick disk than we had in NGC 7814 up here. And then finally, in the bottom, we have another one which has much less dust in it, apparently. You don't see these like lanes that are crossing it in the same way, apart maybe from here. But you also see that the bulge doesn't really look like a bulge. It looks more like a Batman logo, basically, with these spikes out here. And you can also kind of glean them down here if you squint. Actually, now you can, because now I'm not covering it anymore. I apologize for that. But I believe that this is actually a strong bar, more likely than an actual bulge, but there might also be some bulge involved. In any way, this illustrates that even within a relatively narrow category of late-type galaxies, there's still quite a lot of diversity at play. The bulge rotates like the disk, but it is more dynamically warm than the disk. It has more, like a higher level of random velocities of the star's orbits in the bulge than you see out in the disk. This leads to an ellipsoid shape. It is more flat than an elliptical galaxy, but it is more elliptical than in the disk of a spiral galaxy. The light, as we have seen before in our morphology lecture earlier, follows a surface profile that is our old friend from here, from before, where again, RE is the effective radius, which means the radius that contains half the integrated light in this galaxy when we look at it face on. And IE is the intensity at the effective radius. And typically in spiral galaxies, the effective radius of a bulge can be very small and up to a few parsec. However, we also know that the surface index can change a lot between different galaxy types, and this is also true for the bulge. We remember that for elliptical galaxies, the surface index is about 4 typically. And for spiral galaxies or disk galaxies, it is typically about 1, which corresponds to a purely exponential drop-off of luminosity as a function of radius. For bulges, we can distinguish between the classical bulges, as we call them, which are more elliptical-like. They have surface index between 2 and 4. So some of these classical bulges are basically like elliptical galaxies sitting in the center of spiral galaxies, while others are more disk-like and has more ordered rotation, are more dynamically cool. And then we also have what we call pseudobulges, which are shaped like bulges, but have an even smaller surface index, less than 1. So these are way more disk-like and much less ellipsoid-like than the classical bulges are. So this also means that a spiral galaxy typically has more than one surface index. It has a different surface index for the bulge in the central parts and for the disk, which we can see some examples of here. So if we look at the left, we have the SA or SB galaxy, the intermediate between SA and SB type galaxy, which, as we can see, has some quite tightly wound spiral arms and a very prominent bulge. And if we look at the surface brightness profile as a function of radius, we can see that in the center, it is dominated by this very steep, high surface index profile. And as soon as we get out to about between 50 and 100 arc seconds in radius, I don't know what the physical distance here is, but we can see that it is quite well approximated by just a purely exponential drop-off as we get from here and out, where the bulge is no longer dominating. In the middle, we have a SC galaxy, NGC 628, and we can see that this one has a much less prominent bulge. And as we can see in the surface brightness profile, we can see that this bulge it's there in the center, but it is very rapidly dropping off, and we don't need to get very far out before the surface brightness profile is very well described by a simple exponential drop-off as in a typical disk. And finally, we have a dwarf irregular galaxy here, which just doesn't have a bulge. But I find it interesting that despite the fact that it is classified as an irregular galaxy, and you can see that it is kind of irregular looking here, it still dynamically follows the dynamics of a disk galaxy very well, which probably means that the irregularity is mainly visible in because of strong star formation due to a previous interaction or similar, and underneath there's very likely to be a more ordered rotating disk-like but older and fainter redder stellar population that we cannot really see very well in this in this observation here, and probably also quite a bit of an dark or possibly a dark matter halo that also helps stabilize its rotation. Although now I come to think of it, that dark matter halo might not necessarily have given it this disk shape, so just forget about that. Finally, we also have galaxy bars. Many disk galaxies, about half of all disk galaxies, or 50% of all disk galaxies, a little bit more, also have a bar extending from the center and the bulge. So the bar is an orbital pattern. So basically it is a pattern of resonances of stellar orbits in the center. And it happens that it can form when the pattern speed of the density waves is lower than the orbital speed. So this is basically this traffic jam that I talked about before. In this case, stable orbits can form, and when these orbits become stable, well, then you get a long-lived structure, and this long-lived structure is the bar. These bars can help gas flow into the center and maybe even spark star formation or even AGN activity in the center. And they can also help get rid of angular momentum. It is not very well known whether the bar is an evolutionary stage that most galaxies go through, or it just is something that some galaxies will develop, but not all. Here we have a very, very beautiful example of a very strong, large barred galaxy. I don't have much more comments about that, except this is what it looks like. That thing I just talked about before. Isn't it pretty? We'll be talking more about bars in lecture 7 and in its assigned literature. Finally, we also have, and I have to disappear myself here, we also have the effects of the inclination, because when we're looking at these galaxies, of course, they look very different depending on whether we're looking at them face on like this, or we're looking at them edge on like this, of course. But generally, we're looking at them at some kind of angle in between those two, right? And so we need some kind of way to describe or quantify this inclination and apparent ellipticity of these galaxies. And it's important to stress that this is apparent ellipticity. It is not like elliptical galaxies, which are actual elliptical and have an actual ellipticity. These galaxies are more or less circular disks, and the only reason why they look like ellipticals is the inclination angle that they're seen not directly face on. So the inclination is basically defined, the inclination angle is defined as the deviation of the viewing angle from seeing it face on. So if I show myself here again, if we look at the galaxy like this, then the inclination, if we look at the galaxy like this, then the inclination is 0. But if we start tilting the galaxy like this, then the inclination angle grows until it is at its maximum of 90 degrees when we see the galaxy edge on instead. And that should also mean that the cosine of the inclination angle will become the same as the ratio of the minor and the major axes of the apparent ellipse that we are observing in this way, which means that it also practically makes sense to express this in terms of the ellipticity, although again, I will stress that this is an apparent ellipticity, but in projection, it is still an ellipticity, and it is perfectly fine to see it as such, which is defined as 1 minus the cosine to the inclination angle, which means that you have the cosine of an inclination angle of 0 is 1, so the ellipticity is 0, which makes sense because when the inclination is 0, you're looking at the galaxy face on. On the other hand, if the ellipticity is, or if the inclination axis is 90%, then cosine is the cosine of the inclination angle is 1, not 90%, 90 degrees, of course. The cosine is 1, and that means that the cosine is 0, and that means that the ellipticity is 1. So that means basically that the ratio of B over A is 0. So that makes sense. We see just a line this way when we see it perfectly edge on. These are just definitions, just showing them here so that you can learn that they exist. We are going to be using those later on, but we will not be diving deeper in them for now. So that was the end of the second part of this lecture. Thank you for staying with me this far, and I will be seeing you in the next one. Bye.